The next presenter is Zahreddin Hafsi from Tunisia. Please. It seems now that we will have all presentation according to program, except the last one, 1.8. So we will have in row 1.4, 1.5, 6, 7, and we haven't 1.8, Alexander Boritsky and Koleshnikov.
Good morning, all the audience. Thanks, Professor Jukic. And also, I have to thank all the audience today. Sorry for so much. Okay. So I will be presenting this paper entitled Hydrogen Embrittlement of Steel Pipeline During Transient by me, Zahreddin Hafsi, from the National Engineering School of Sfax, Tunisia. And actually, this numerical work was done in collaboration with the Indian Institute of Technology, Europar, and under the guidance of both Professors Manoranjan Mishra and Professor Semil. Just to go quickly to save a little bit of time, the presentation will be divided into 4 parts. I will start by an introduction. Why we are talking about hydrogen embrittlement of steel pipelines during the transient, and which kind of transient we'll talk about. Also, we'll introduce the mathematical formulation. That means the equations that governs both phenomena of gas flow and hydrogen diffusion into the steel pipeline. And then we'll solve numerically these equations using COMSOL multiphysics software. Somehow a coupling approach will be presented. The numerical results also will be validated by some theoretical results. And we'll discuss why we are talking about hydrogen gas. Because of its wide range of usage. Actually, hydrogen gas nowadays is used as fuel for rockets, in electricity production, in some chemical processes, several chemical processes actually, in battery fuel cells, and also as a fuel and clean fuel for cars. So we have a need to transport hydrogen in somehow large scale. That means from the site of productions to the sites of consumptions. So several methods was adapted, transportation by train, by trucks, by boats, and by pipelines, which is a very cost-effective solutions for large-scale transportation. So the transport of hydrogen gas through pipelines is the best option, of course, but let us see some maps of hydrogen network, hydrogen gas pipelines network in the world here in Europe, the hydrogen gas network. But let us compare with natural gas network. Actually, we can see that natural gas network are well developed and in the world. So if we will give some figures, we have about 4,500 kilometers of of hydrogen pipelines, and compared to almost 2 million kilometers of pipelines designed to transport natural gas. So the idea is almost clear, is to blend hydrogen gas in existing natural gas pipeline. Somehow a cost-effective solution, a genuine idea maybe, but of course there are some limitations due to what actually? Due to the difference in thermodynamic properties between both gas, H2 and CH4, that may lead to condensation of hydrogen. Also, if we will inject hydrogen into a pipeline designed to transport natural gas, there will be an increase in the velocity, some overpressure values that may damage the structure of the pipeline. And also our topic today is the embrittlement of the steel pipeline due to what? Due to the diffusion of hydrogen inside the lattice structure. So there will be, we'll be facing a risk of hydrogen leakage, and all of you knows what does it mean, a hydrogen, or pressurized hydrogen leakage, somehow a catastrophic incident. Just to summarize a little bit, the transient gas flow in steel pipelines will lead to somehow overpressure values, and these overpressure are considered as an internal load on the pipeline wall, and this will induce the diffusion of hydrogen in steel material. That's why we're talking about hydrogen of steel pipelines during transients. So equations that govern these phenomena, we are presenting two physics actually. That one related to the gas flow in steel pipeline governed by continuity and momentum equations. And the second physics that deals with the non-steady diffusion of hydrogen in steel microstructure, the famous equation of Fick's, the second law of Fick's. So here we have actually three parameters or three variables that are not coupled. Pressure and velocity are already coupled, continuity and momentum, but the concentration of hydrogen is not coupled to the other two variables. So two physics, three main variables, and we need to find a coupling equation that relates either concentration to pressure or concentration to the velocity to somehow close the system, let's say. So coupling equation will use the relationship between the solubility of hydrogen gas in steel and the concentration of this hydrogen molecule. Using the Seibert's law, if we will combine both equations, we will find somehow relationship, and an Arrhenius type law actually that gives the relationship between the concentration of hydrogen atoms in relationship with the pressure of hydrogen gas. So to summarize, two equations for gas flow in pipelines, one coupling equations, and then the equation of gas diffusion in steel metal, and this is the whole mathematical model that needs to be solved. We'll solve it numerically using the finite element-based software COMSOL multiphysics, version 5.2 actually. So we have two different physics. Pipe flow module, we will use that PFL module. It's let's say a pre-built module in COMSOL itself. And to solve the gas flow equations in 1D domain. And we will use another physics called the TDS, transport of diluted species, in which we can solve the diffusion equations. That means the second law. And we will combine both physics. We'll couple both physics to find somehow a solution. As a case study, we are talking about somehow long pipeline of 80 kilometers that transport hydrogen gas. This pipeline is of diameter 0.6 meter, and there is a delivery pressure of hydrogen of about 70 bar. So the pressure drop resulting from COMSOL here 70 bar, it will drop a little bit, the pressure reaching almost 56 bar. And in transient case, if we will be having at the outlet of the pipeline a varying hydrogen demand over 24 hours, that means the consumption of hydrogen is varying with time. We'll be having this variation of pressure as a result. And this variation of pressure is the outlet of the first physics, that means the gas flow, and it will be the inlet of the second physics. It will be taken as a boundary conditions, that means the boundary load applied to the internal wall of the pipelines. What we will do actually, we will just transform this evolution of a pressure into an evolution of the hydrogen concentration using that coupling equations we have talked about. So this concentration, the profile of the hydrogen concentration, is an internal load into the pipeline wall, and we are taking just, let's say, the half of the pipeline. We have been able also to take only the quarter of the pipeline due to the symmetry of the problem. So this is, let's say, the boundary condition of the second physics. We will be considering for the first time API X52 pipeline still. And then we will compare with two other kind of material, API X80 and netrided API X52, and we will be having some different diffusion coefficients. So, okay, I will just go. So as a result here, when solving the diffusion equation, we will be having this shape that gives the evolution of the concentrations in the pipeline wall. So we can see that the maximum of concentration in the internal wall, then the concentration is decaying, then it will reach somehow, let's say, if it will be 0 or not. Actually, this shape is the solution of that equation. But this equation has already analytical solution for a one-dimensional flow. It's written under this form. It exists in literature. So if we will compare the numerical solution with that analytical solutions of the profile of the concentration that goes from the inner boundary to the outer boundary, the concentration of hydrogen is decaying, and it will reach somehow 0 value. Actually, it's not 0 exactly, we'll look for. Just here to validate our numerical model with the analytical solution and to go further to test the other two materials, that means API X52 netrided and API X80. So these are the shapes of, or the profile of the concentration for the three materials, X52 base metal, X80 and X52 netrided. If we will do a zoom, I don't know, I will try to, here. We'll do a zoom here in the outer surface of the pipeline to check if the concentration of hydrogen is equal to 0 there, if we are in safe condition or not. So if we will do a zoom, we will observe that for X52 material, there is an amount of hydrogen. The concentration is not equal to 0. You can see here. And here, the for other two material, it's okay. It's equal to 0. Just to quantify this observation, we are calculating what we call the permeation depth. To what extent hydrogen will permeate into the pipeline wall, if the wall was of infinite dimension. So if we'll calculate the permeation depth, for X52, we find 13 millimeters, sorry. It exceeds actually the thickness of the pipeline. That means we are not working in safe condition, and we have actually hydrogen leakage. Hydrogen is escaping from the internal wall of the from the wall of the pipelines. And for the other two material, it's okay. 6 millimeter and 8 millimeters is okay. Hydrogen is diffusion, but there is no leakage. So what are the solution actually? Why we were talking about the API X52? Because API X52 is widely used for natural gas pipeline. I will think to use these pipelines to transport hydrogen. Almost 25% of natural gas pipeline are made up of X52, according to Capella in 2018. So API X52, it can ensure the safe condition of natural gas, but there is a risk of leakage when thinking of hydrogen condition. So what are the solutions actually? What we can do is, we can use natural gas installation to transport hydrogen, but not for 100% of hydrogen. We have to control somehow the amount we can inject, the amount of hydrogen inject. And this work is already done in France. There are some experimental work done there, also in UK, I think, and in Germany, I'm sure. So we have to control the proportion. Or to avoid hydrogen embrittlement, we have to build pipelines using higher grade API steel material. Or also we can use common grade material like API X52, but after some chemical process like hardening or somehow. Because these kind of processes reduce the diffusion coefficient. Or we can proceed, I think we will not talk about actually in details, we can proceed with coating of pipelines, either internal wall coating or external wall coating. Because when coating, we will add a layer of a coating layer, and we will be talking about two-stage diffusion.
hydrogen needs to diffuse through the coating layer, then through the base material itself. And somehow we will reduce the diffusion of hydrogen. Just to conclude quickly, we were talking about the pressure-induced diffusion of hydrogen gas, because that diffusion was induced by the transient pressure evolution of the gas. We solved the second Ficky's law. We were using COMSOL multiphysics, and we confirmed our results that's by analytical solutions. The use of X52 base material is risky because of what? Because of overpressure values that may damage or break down the pipelines, and also the leakage of the hydrogen, as we have seen. So we can opt for using higher grade still pipelines, material pipelines, or nitrided material that can reduce the permeation of hydrogen. The effect of the coating will be normally studied in details for our next projects. Just before finishing, I need to acknowledge National Engineering School of Sfax, Tunisia, our lab in the Institute of Technology, Europe, the lab. I did an internship there. The NAM Science and Technology Center in New Delhi, India. And of course, EC for its financial support that allowed me to be here today and to talk about such things. Thank you for your attention from Zaidin of Tunisia. Thank you.